Okay, yesterday I discussed a little bit the basic elements that guide you to the selection of the, say, the switching frequency Fs for the switches inside the full bridge, the H bridge of the inverter, one-phase inverter. Okay, once Fs is chosen, and so we have MF, which is the frequency modulation factor, which is Fs over F1. So once Fs is chosen, this factor is computed, okay, because F1 is the fundamental component we want to get at the output. And this is the switching frequency. So some of the characteristic of this DC to AC converter depends on the value of this MF and on the fact that this MF is, for example, an integer number, or maybe it's not an integer number. We already saw something related to this specific say, behavior of the MF factor. For example, when we talked about the unipolar pulse width modulator and the bipolar pulse width modulator. Remember that the output spectrum of the output voltage can be a little bit simplified if we choose, for example, MF to be an even number. So an integer, which is also an even number. Okay, for example, we can simplify a little bit the harmonic content, eliminating some of the harmonics, the high frequency range of the output voltage spectrum. The same happens for the bipolar pulse width modulator. Okay, in the bipolar pulse width modulator, for example, some simplification of the output spectrum will be obtained by using an MF, an integer number, and also an odd number. Okay, so this kind of simplification that can be useful to make easy the modulation, the filtering of the output voltage in order to, say, increase the quality of the sine wave that you want to get at the output. So, say, reducing the total harmonic distortion, for example, can be only obtained when MF is an integer number. But MF integer means that the ratio between the switching frequency and the fundamental of the output component you want to get at the output is always, let's say, an integer number. But one of the main requirements of having a switch mode DC to AC converter is that I can use a set of control signals provided to this converter in order to modulate the electrical characteristic of the output voltage. For example, the output voltage and the output current of the inverter can be modulated in terms of, say, changing the amplitude of the output voltage, or maybe changing the frequency. Okay, so here, this characteristic can be, say, variable. Okay, for example, F1, so the harmonic content, the frequency of the fundamental of the fundamental component of V1 or V naught fundamental component is changeable. Okay, depending on the characteristic I want to obtain at the output that are more suitable for driving my motor. Okay, what happens when I change F1? If I change F1, in order to get an integer number, of course, I have to change also the switching frequency, okay, in order to get the ratio always an integer number. Of course, this can be difficult because my control loop, which provides this control signal on the basis of, say, the measurement of what happens at the output of my inverter, have to change accordingly to the variation of the frequency F1, also Fs. This kind of, say, discussion can be typically discussed in terms depending on if the value of MF is very large or it is not so large. Okay, in literature, this can be discussed by looking at the value of MF, indicating some specific threshold. Okay, in the literature, you can find that if MF is, say, lower than 21, which is somewhat it comes, this number, from say specific analytical techniques that you can find, I think, in the book of Professor Mohan. He wrote a book on power electronics, which is very huge, including all about power electronics. A little bit complicated in my view. And in the book of Professor Mohan, you can see exactly this kind of derivation in order to find out this threshold. Okay, that separates MF large number or lower number. Okay, for MF which is less than 21, this is indicated are, say, MF which are, say, having low value. This means that, for example, if the output frequency that you are, say, using at the output of your inverter is as low as 50 hertz, okay, so tenths of hertz, it means that Fs should be less than 1 kilohertz. Okay, so anytime you have a switching frequency which is less than 1 kilohertz and your output frequency of the inverter is in tenths of hertz, that you have this MF here, which is considered to be low value in this discussion. But anytime you have MF which is not very high, for example, let me consider 21 as indicated by Professor Moore, but this discussion can be, say, generalized with low value of MF. What happens? Basically two things. The first one is that if MF is not so high, like in this way, then it means that Fs is not so high with respect to F1. And so this implies a difficult in, say, demodulate what happens at the output, so to filter out high order harmonics. Okay, so first of all, the quality of your output, your sine wave, is a little bit distorted due to the presence of, say, large high order harmonics in the spectrum. The second consequence of this not so high value of MF is that if MF is not an integer, okay, like for example the requirement I have discussed before, MF even or odd, depending if you are in a unipolar or bipolar modulation respectively, in order to simplify your output spectrum. If MF is not integer, in the case you have low value of MF, then what happens is that you have sub-harmonics. Subharmonics are specific harmonic content that you could see if you look at the spectrum of the output voltage appearing at frequency lower than F1. So you have something like, say, appearing here. These are subharmonics. So harmonics at frequency lower than F1. Of course, you have all other frequency content, intermodulation product, etc., etc. Of course, the presence of subharmonics represents a, say, drawback, because if you want to filter out this harmonic content in order to isolate just what you want to get at the output, assign weight with frequency F1, This is not possible using low-pass filter, okay? Because low-pass filter, of course, take into account all the low-frequency content in this bandwidth, and so it has also the subharmonic content to be, say, not easily to be filtered. So in that specific situation, anytime you have, say, MF which is not so high value, for example, less than 21, so you need to synchronize Fs and F1, meaning that the ratio should be always an integer number. So needs for synchronize Fs and F1. Okay. If you want to eliminate these subharmonic, because if you have an integer number as MF, then the subharmonics are not appearing, and then this come to be not a problem. Okay, so this happens for MF very low. When MF, let's say, is higher than 21, so it means that this switching frequency is higher than 1 kilohertz. If F1 is 50 hertz, for example, this is just an example giving you some, say, direction numbers. Here it happens that the frequency Fs is larger, is much larger than F1, 21 times, say, bigger. This make possible to have the possibility to make easy the filtering of the output. So first consequence is that filtering V naught of F is, say, easier, and so the quality of your output voltage is a little bit increased, so you have a total harmonics distortion which is lower than the case we studied before. And the second consideration is that even if you have MF which is not an integer, subharmonic amplitude occurs, of course, subharmonics appearing here, but the amplitude of these subharmonics is minimized. They are very low. The amplitude subharmonics are low. So this means that in that specific situation when MF is large, the control does not need to, let's say, operate in a very complicated way to eliminate these harmonics. Okay, you can accept it because their impact on the distortion of the output voltage is minimized. Okay, so you can have MF which is also not an integer number. Okay, so in that situation, there is no need to synchronize. Okay, here there is no need to synchronize Fs and F1. Okay? Basically, it means that you can change F1 without changing Fs. That can be, say, fixed. Okay, so Fs can be what you have for your power devices. Okay, for example, if you have MOSFET, you can have 100 of kilohertz, and you set this frequency fixed, and you can change F1, modulating it according to the characteristic you want to get at the output. Okay, the characteristic more suitable for your load. Let me just discuss a little bit something that we already discussed previously about DC-DC bidirectional converter, and this is the ripple in the inverter output. What is the ripple? Okay, we learned that the ripple is the AC component that you have superimposed onto the DC quantity, okay? Referring to the DC-DC discussion we had previously during this course, we always consider in the ripple the AC contribution, and which is totally separated from the DC, the quantity at the output, okay? Basically, we can extend this discussion considering the ripple as a repetitive waveform that comes out as the difference between the instantaneous value of the waveform and its fundamental frequency component, okay? Not just the DC contribution, but the DC is now comes, there is no DC at the output, basically because we are talking about DC to AC. But if you take the difference between the instantaneous value of the, for example, the current you have at the output and the fundamental frequency component, that current, what remains is called the ripple, okay? So let's just considering the ripple for the inverter, and this discussion, let's say, basically is performed in the same way we did for the DC-DC converter, okay? The difference is that we have to face, to consider the ripple as the difference between the fundamental frequency component and the overall instantaneous component of the current, for example. Okay, let me put this VD, CD, constant voltage. Then here you have your inverter. For example, the full bridge, single phase inverter, you have the output. And for example, you can have at the output connected the AC motor. Let me represent the AC motor by the standard, say, equivalent circuit that you can see from their supply terminals, that is made up of inductance, okay, which is the winding inductance of the phase the inverter is driving, and then you have also here the back EMF. The back EMF, of course, now for AC motor is something that is a sine wave. Okay, it's not more a DC quantity. Is a sine wave having a component at the frequency F1 I want to obtain at the output of my inverter. This voltage here is the voltage V0. The current here is the voltage I0. Here in series with the inductance, you can have also the resistance, okay, with, let's say, represent the model of the ohmic losses in the winding. This is what happened for, say, generic inverter. Remember the superposition, say, effect that we considered when we talked about the ripple in DC to DC bidirectional converter. Okay? We separate two different circuits in which in one you have just the, in that case, DC quantities, okay? And this is related to something which is, let's say, constant, not involving the ripple. And another circuits in which we have just the AC contribution, okay? Just which is not having any average value. The average value is null, okay? So DC and AC. Here we can have the same reasoning, okay? But extending our discussion here, we have no more DC. You have a fundamental component and something which is, let's say, not at fundamental frequency. So we can divide these, we can separate this discussion here, including again two different circuits in order to analyze the ripple. One circuit is now not at DC, but at the fundamental frequency. So this is the circuit at fundamental F. So this is what we call so far F1. And so let me put this A and B node here. I can use an equivalent voltage at this node, and this equivalent voltage here represents the fundamental frequency component of the output voltage, and we call this V naught 1. Okay. Then we have the inductance. Then we have the resistance of the motor, And of course, we have the back EMF, because the back EMF is again a sine wave at frequency F1. For example, let me put back EMF as a sine wave having amplitude E0 sine omega 1 t. Okay, this is the back EMF. So this is E0 sine omega 1 t. LR, what is the current flow in this circuit, is the fundamental frequency component of the current. And then we have another circuit, which is the circuits that let's say is basically is the difference between the total current you can have, or the total voltage, and the fundamental component. So this is the circuit for the ripple. Between the same node, I have, say, a voltage here that called V ripple, inductance, resistance. And what about the back EMF? The back EMF is just a sine wave at frequency F1. So it is at the fundamental component. So here you don't have anything in this circuit here. Okay. R, the current flow in this circuit, is the ripple of the current. It contains no more fundamental component. Okay. Like the V ripple here does not include any component at frequency F1. Okay, so for example, V0 instantaneous value is a voltage that can be, I don't know, something like this. Is a sine wave modulated like this. Okay, this is V0. V0 depends if you are using unipolar pulse width modulator or bipolar PWM. So you can have different waveform, but basically you have a rectangular waveform with amplitude is changing, is modulated by a sine wave. Okay, so if you look at this voltage here, you can extract, say, the fundamental component of this waveform, and the fundamental component will be as a sine wave like this, etc., etc. So this is V not fundamental component. Okay, so my circuit here is a circuit in which you have the fundamental component, let's say here, so a sine wave, which is the red curve here, and then you have the ripple, which is, say, the ripple here is the difference between the total instantaneous voltage V0 here and the fundamental component. So we can write that V0 T basically is the sum of the fundamental component plus a summation, okay, an infinite sum of all other harmonics. Okay, and the same happens for the current. Is a summation of a fundamental contribution plus all other harmonics. So basically we have V0(1), the fundamental frequency component, plus the ripple. Okay, so basically the ripple includes the contribution of all high order harmonics that you can have in the circuit, in the voltage or in the current. So what about, for example, so the ripple that you can have in the current, okay, the current ripple here. As we did in the previous discussion about the same topic in the DC converter, basically remember that I say neglect the resistance instead with inductance, because basically it makes the computation a little bit easier, okay? And in this situation, you can see that the voltage across the inductance, VL, is basically the same as the ripple voltage. And so, which is the current ripple, but if I know that VL is the I ripple over the T, because this is the characteristic of any inductance, and VL is exactly V ripple, basically, okay, as we did before, then I know that I ripple is 1 over L, the integral of the voltage across the inductance. So in order to derive the ripple, this can be, let's say, it can be regarded as an extension of what we already done for DC-DC converter. Okay, basically this is the equation. Can be using this equation you can also get the previous result about DC-DC converter. But as you can see here, the ripple in the current depends on this integral here. Okay, so basically depend on the area that you can have in the time domain waveform of the ripple voltage. Okay, on the area that you can have, let's say, looking at the difference between the black curve here and the red curve. So the difference between the total instantaneous voltage and the fundamental frequency component of the same voltage, for example. The difference is the ripple. Just to give you an example, in order to, let's say, estimate the ripple in the current for these inverters, let me share the slide, because in the slide I put some well done waveform. Okay, you should see something here. This case is for the bipolar pulse width modulator. As you can see, the voltage V naught in the top side of this page is okay, here is the top side is basically the output voltage, instantaneous value. This output voltage ranges from negative VD to positive VD. And so it is the typical behavior of a bipolar pulse width modulator. But of course, you can do the same for the unipolar one. And you can see also that in the same plots, you have the fundamental component of the same wave, okay, V naught 1, which is a sine wave, having a specific period. As you can see, the width of the output voltage is sine wave modulated, okay, when the sine wave, when the fundamental component is, let's say, reaching the peak, the width of the waveform is larger, etc., etc. Now, if you get the difference V naught minus the fundamental component, which is reported in the second plot here, in the middle plot, you can have the ripple. Okay, now the ripple is defining this way for C quantities. Okay, what about the ripple in the current? But the ripple in the current depends on this integral, which is reported also here. And this integral depends on the area under the ripple curve. For example, as you can see that in the first step you have here, in the first, say, time interval, you have this behavior. If you look at the area under this quantity here, the area here is, let's say, less than the area you can have in the second pulse here, or is higher than the area you can have in the third pulse. This means that the ripple, the peak-to-peak current you can have, for example, is larger during the first peak respect to the second pulse and the third pulse. And this happens exactly in this way. As you can see, the peak-to-peak variation, the ripple, the result of this integral is, say, larger here due to the large area under the V-ripple curve with respect to the second pulse and respect to the third pulse. In this region, in which the V-ripple basically is very small, it tends to be zero almost, the ripple is, let's say, very small here. So also the ripple is not constant. The ripple has a variation which is something like this. Okay, computed by using this interval, and a roughly estimation can be done just by looking at the area under the ripple curve, which is also the voltage across the inductance. This is just the ripple, okay? It's not the overall instantaneous current I naught you have at the output. It's the ripple component. But the output current, as I showed you before in the whiteboard, the I naught current is the summation of the fundamental component I naught 1 plus the ripple current. So in order to find out which is the total instantaneous current I naught, I have to sum this ripple behavior I found out in this way to the fundamental component of the current. Okay, this is done here. Okay, again, this is the plot for bipolar pulse width modulator, so exactly the same curve I showed you before. You can see this the output voltage ranging from negative VD to plus VD. Superimposed on this blue curve, there is the fundamental component of the output voltage, the orange curve here, which is a sine wave. And then you have also the I naught current. As you can see, the I naught current is again a sine wave. It's a little bit, let's say, delayed because you have a, say, inductive ohmic load. So current and voltage V naught and I naught are not in phase. The current lags the voltage. And you can see there is that, say, I don't know, green curve, which is a sine wave. And this is the fundamental component of the output. And superimposed on this fundamental component, you have this sawtooth waveform, dark green curve, which is the ripple we previously derived. As I showed you before. Okay, as you can see, the ripple is not constant. The ripple changes depending on, let's say, the previously computed waveform. Okay, so this is the expression of the total output voltage, instantaneous voltage, V naught over T, which is the blue curve, rectangular waveform, sine wave modulator, and the overall I naught current, which is basically a sine wave with this ripple on it. As you can see, the current increases when the output voltage is positive or decreases when the output voltage is negative VD. Okay, because this is always the same behavior. When the voltage across the inductance is positive, okay, basically you have a di on the T, which is positive, so meaning that you are increasing the current. When the voltage is negative, is meaning that di on the T is negative, so decreasing current occurs. Okay, you have this sawtooth waveform, they rising up and down in different ripple, say, with different amplitude, depending on the ripple computed here. For example, the ripple is very small when the output voltage fundamental component is at the higher level, because the difference basically is small. And as you can see, this is exactly what happens here. Okay, when the orange curve, which is a fundamental component, is at the higher part, the ripple, the green curve here is very small. Conversely, when the orange curve, okay, which is a fundamental component of the voltage, crosses zero, for example here, the ripple in the current is as the highest value due to the fact that the ripple voltage is, say, very large. Okay, I hope that this, say, can be it's clear. If you have questions, of course, I can answer your question. Let me just move to another topic, okay? And in order to discuss this topic, I have to use the whiteboard. Up to now, we talked about the linear pulse width modulator. Basically, in this linear pulse width modulator, we learned that the amplitude of the fundamental component linearly increases for increasing amplitude modulation factor. Ranging from 0 to 1 MA means that the amplitude of the fundamental component of the output ranges from 0 to VT in a linear way like this. So this is what is called the linear pulse width modulator we talked so far. And the maximum amplitude I can get for my output frequency component is exactly VD, the input voltage source. What happens now if I leave these constraints, so having MA up to 1, and I try to increase a little bit the amplitude, and so the dynamic of my control voltage exceeds the dynamic of the triangular waveform. So this is called the overmodulation. It occurs for MA that are larger than 1. Let me consider this overmodulation, looking at what happened at the modulator. Okay, the modulator has the triangular waveform like this. This waveform has a fixed frequency, for example, Fs, and it also has a fixed amplitude, which is the peak value of the triangular waveform. Okay. So up to now we are talking about the control voltage, which cannot exceed, say, the peak of the triangular waveform. The control voltage is always within this dynamic. Now I'm discussing something that occurs when the sine wave is free to exceed the amplitude. Okay, my drawing is not so good, but I hope that you catch the meaning. Okay, this is a sine wave, this is the control voltage, but now the peak-to-peak value, let's say here, so 2 times V control peak is larger than V triangular peak value. So MA is larger than 1, if you want. So let me consider what happens, for example, in terms of unitary switching function. So QA here. QA both for the modulation, the unipolar pulse width modulation, or also the bipolar pulse width modulation is always obtained in the same way. You have to look at the control voltage, which is also the control voltage for the leg A, and then you have to consider the comparison between the control voltage and the triangular wave. So here you have 1, then you have 0, then you have this waveform up here. From this point on, you have always 0. Okay, so this means that you have TA plus here on, TA plus also here, TA plus here. What happens to QB? For QB, you have 2 different behaviors depending if you are considering unipolar or bipolar pulse width modulator. If you are considering the I don't know, the unipolar one, okay, unipolar pulse width modulator, then the control voltage for the leg B is derived by the control voltage of the leg A minus the triangular, basically the triangular peak value minus the control voltage, okay, and you what you get is exactly the symmetrical waveform with respect to the the control with respect to the mean value here, the triangular peak divided by 2. Something like this, okay? So here you can have the classical comparison. And then you have always this behavior here. Something like this, not to be so precise, but anyway, to give you, say, the basic idea. The difference between the two multiplied by the voltage VD give us the output voltage waveform. Something like this. Okay. So you get there, you have TB plus on. Also here you have TB plus, etc. So you have here the region which you have TA plus and TB minus, and here you have the region which you have TB plus and TA minus, and then you have some other region. This is what about V naught. Let me consider also what happens for this is for the unipolar modulation. So my discussion, nothing changed with my previous, say, results about unipolar pulse width modulation. I have also only to think about the fact that there is a large portion of the control voltage, which now is, that comes from here, that is larger than the peak value, or say lower than 0. So this has a direct impact on the output voltage. Okay, the output voltage is not exactly like before. What happens for the bipolar one? You have triangular waveform like this. I have something like, I don't know, something like this. Sorry for my bad drawing. I hope that this not confuse you the idea, but this is, say, the triangular waveform and the control voltage. We are talking about bipolar pulse width modulation. What happens for QA? Nothing changes with respect to previous discussion. We have to consider the comparison between the two curves, and then we have something like this. And here you have the, let me just extend a little bit this waveform, 0, 1, and from this point on you have, for example, 0. Something like this. QB is obtained by using the same control voltage, okay, but say inverting the law by which I can generate QB. So it means that I have, for example, here 0, 1, 0, etc. Is the complementary waveform with respect to the previous one. So you have here, you have TA plus, TA plus, TA plus on, and here you have TB plus on, TB plus on, TB plus on. Okay, so the difference is again the output voltage, V naught over T. And it comes out the standard bipolar waveform. something like this. Okay. We can say that my drawing is not perfect, but anyway, we have this region which we have TA plus, TB minus, and then we have a TB plus TA minus on etc. Negative VT plus VT. So basically, in this discussion, what I can stress is that here you have a large portion of the control voltage that is allowed to, let's say, exceed the peak value of the triangular waveform. What does it mean, this in terms of comparison between a control voltage and a triangular waveform? That in this region here, we have no possibility to use the comparison between the control voltage and the carrier waveform, the triangular waveform, in order to modulate the unitary switching function width. Okay, even if in this region here the control voltage is changing, okay, it's not constant, this variation of the control voltage is not taken into account in the unitary switching function. Okay, as you can see here, the unitary switching function has no, let's say, any idea of what happens about the control voltage. The only thing that he knows is that the control voltage is higher than the peak value of the triangular waveform. But there is no, say, variation, no modulation of a pulse width depending on the variation of the control voltage. Okay, basically, in the linear pulse width modulator, this variation is always a direct consequence, the variation, the modulation of the pulse width modulation. Okay, so always I can take into account, say, the modulation of the sine wave. Here in the over modulation, I lost portion of the sine wave because this waveform is something higher than the peak value of the triangular waveform. This happens for both the modulation. Okay, here you can see that you have no variation at all of the output voltage, taking into account what happens to the control voltage, and even in the bipolar pulse width modulation, in the large section in which you have, say, this peak variation here, you connect not any, does not impact pulse width modulation of the output. You have just constant behavior, okay, having a specific switch contribution. If you look at the output fundamental component, okay, so if you look at this waveform here, the output voltage, and you use the Fourier transform to look at the several components in frequency of this waveform, you can see that there is again a component at frequency F1, which is the frequency of the control voltage. Say you can see that there is a, say, contribution like this, which is V01. In the same way, for the bipolar pulse width modulator, if you look at, say, at the composition, spectral decomposition, you can see that there is a control voltage, a voltage, which is the fundamental component of this waveform, which is a sine wave at frequency F1, exactly like the control voltage. And another behavior is that not only you have, again, a fundamental component at frequency F1, but the amplitude of this component here exceed the voltage VD, which is here. So you can see that the amplitude here, so the peak value of the fundamental component, could be is higher than VD. Also here, the peak value of the component at frequency F1 is higher than VD. So this means that if with the linear pulse width modulator, in which my control voltage is vary within the dynamic of the triangular waveform, the maximum amplitude that you can have for my, let's say, fundamental frequency component of the output at the maximum is VD. Using an MA which is larger than 1 makes possible to increase the peak value of the output component. So if you want to consider the overmodulation in the same plot, I can see that you have something like this. So you are, say, increasing the peak value of the output component. But the variation of the peak value you can get at the output at frequency f1 is no more a linear function with respect to the MA. Okay, so as you can see here, the variation is something which is not linear, like in the linear or so-called sinusoidal pulse width modulator. Okay, why it can be useful to have a fundamental component at the output voltage which is larger than VD. VD, remember, is the constant voltage that is applied at the input side, DC side of my inverter. It can be useful in some specific application in which for example, okay, not limited to my example here, but this is basically the most important of this application, which the input DC side of my inverter is obtained by using, let's say, a rectifier from an alternate mains voltage source. Suppose that you have here an alternate function. You need a AC to DC converter, so a rectifier, okay, to obtain here across the CD voltage, CD capacitor, a voltage VD, which is basically constant, okay? So my input, DC input of the inverter is not, say, a DC source like a batteries or solar cells, fuel cells, etc. It come out from the rectifier, okay? So supposing that you have 230 volt RMS as the basic mains here, when you rectify this voltage at the output, the peak value of the output rectified voltage that you can have basically is not 230 RMS voltage. It's something less because you have some losses inside. Okay. For example, if you use here a, let's say, a diode rectifier, Gretz bridge, whatever, then you have to take into account the small losses due to the voltage across diodes that are on. So the voltage VD here at the maximum is a little bit less than 230 volt RMS. Now, suppose that you have the case in which your inverter should supply a voltage to a, say, AC motors, and this voltage, nominal voltage, should be exactly 230 volt RMS voltage here, okay? What happens? What if you need exactly 230 volt RMS, but if you need this voltage here, using linear pulse width modulator, at the maximum you can obtain the input voltage VD, okay, which is a little bit less than 230. So you need to increase a little bit your fundamental component at the output. And the only way to do that is to increase MA over 1. So you have something which is higher. Okay? So for example, this can be a situation that can be useful in using the overmodulation. What happens in the overmodulation, say, output spectrum, okay? Because we know what are the standard spectrum for sine wave pulse width modulator, linear region, okay? F1, then you have intermodulation products around Fs, around the second harmonic Fs, etc. Then we can simplify a little bit by using specific MF value, etc. But here the situation is totally different because now we have no more that kind of situation. If you decompose the output voltage in terms of, say, harmonic components, you can see something like this. Let me just answer the questions. From Moles, can you repeat this concept of the modulation in rectifier? Okay, I'm just justifying why we are interested in having a peak value of the fundamental component of the output voltage to be higher than the input voltage VD. Okay, so a possible application. And I discuss this application here in which my inverter has the input which is obtained by the rectification of an alternate AC waveform, okay, by using rectifier. Supposing that I have 230 volt root mean square value of the sine wave at the input, when you rectified it, the voltage VD, constant voltage, that you can obtain here, okay, is something that is not able to reach exactly 230 root mean square value, but something less, because you have, for example, diode in the bridge rectifier. You have losses. And so basically, this is not the same. It's a little bit less, can be, I don't know, 215 root mean square value. So if we are in this situation, exactly like I described here, and my motors here, my load requires as a nominal voltage to be supplied exactly, say, 230 volt root mean square value, I can obtain it. Because at the maximum, as I told you before, in linear pulse width modulator, I reach VD when MA is 1. Okay, but VD is less than 230. But I need 230 for my motor. What I can do, I have to increase MA over 1 to, say, exploit the feature to get higher peak value of the output fundamental component. Is it much clear? So the output spectrum is something like this. You have F1, okay, exactly the frequency you need to get at the output. Then you have all the harmonics, like for example, 3F1, 5F1, 7F1. Basically, these harmonics are reducing in amplitude, increasing the frequency. Okay, that suppose that you have, I don't know, your MF is 9, so that means that the switching frequency is 9 times the frequency F1. So you are, say, 9 F1 here. This is Fs. Okay. So what happens here is that this harmonic here a little bit higher. Then you have 11. So you have this behavior, which the amplitude is decreasing, except in the region around the frequency, which is, let's say, Fs. Basically, it comes from a mixture between a perfect square wave having duty cycle 50% and the behavior of the pulse width modulator in a linear region, which you have intermodulation product around Fs. Okay, you have something like this. Basically, this harmonic content, this amplitude here, could be even less than the amplitude you have in a pulse width modulator. So this can be something that helps you in not having too much losses at the output. But basically, if it is a little bit too difficult to isolate F1, because the first harmonic you have to filter out is the third harmonic, okay? And so my filter action should be very steep in the interval between F1 and 3F1. So basically this happens in the Doppler modulation. Maybe the amplitude are not so huge with respect to the sine wave pulse width modulator, but the filtering is a little bit complicated, except for all application which you are not worried about, say, the quality of your sine wave, and then you accept having total harmonic distortion of the output voltage which is not so low. Basically, all the application which you can accept a ripple in the torque, maybe all the application which are not so important, vibration or noise, etc. Okay. Basically, the basic behavior here, the basic advantage is to have a amplitude fundamental component that is a little bit higher than that you can have in the linear, higher than Vd. What happens if I continue to increase MA? Okay, if I continue to increase MA, so look, for example, here, it means that, for example, I have this behavior here. Okay, so I continue to increase this wafer, okay, or in the bipolar pulse width modulator, I continue to increase the peak value of the, say, fundamental, or the control voltage here. So I'm increasing MA. If I'm increasing MA, what happens is that the part in which I lost the possibility to compare the control voltage with respect to the triangular waveform enlarges. And so it means that, for example, this part here, in which you have a constant behavior, it becomes wider. Okay, you add this part here. And the same way happens for the bipolar one. If you increase, then you have, say, that the part in which you are losing, say, the possibility to have a modulation of the pulse width is enlarging. This part is enlarging. Okay, so this means that this part is enlarging here. So a point eventually is reached in which you have no more comparison between the control voltage and the sine and the triangular waveform. For example, if I increase the MA up to this point, okay, as you can see, I have basically no comparison at all. Okay, the control voltage for all the T1 over 2 is always higher than the triangular waveform. So it means that this part here is so large, this part here, that it covers all T1 over 2. So this part here covers T1 over 2. So basically, I want to describe this feature in a new page. Okay. Continue to increasing MA, a situation happens in which, if you look at the control voltage, and now I know that my drawing will become very bad, but something like this. Okay. QA, it becomes, let's say, like this. This is T1. Okay, so for T1, you have T1 over 2, in which you have TA plus, and the other half of the period in which you have TA minus. What happened for QB? But QB depends if you are using unipolar or bipolar pulse width modulator. And if you use the, for example, unipolar pulse width modulator, means that you have to consider the, say, symmetrical wave from respect to this one. And you see something like this. TB minus, TB plus. And what about the output voltage? The output voltage, V naught, is the difference between the two. And the difference between the two is basically a waveform like this. TA plus, TB minus, TA minus, TB plus. VD, negative VD, this point is T1 over 2. This is for the unipolar pulse width modulator. What happens if you use the bipolar pulse width modulator? Something changes? Absolutely not. you have the same behavior. In the bipolar pulse width modulator, you have to think about that this is the control voltage for the leg A and B, and then you have to choose, say, the opposite rule of generation, and so you have exactly the same behavior. So when MA is a value which is MA, let's say, called star, so that V control intersects V triangular, let's say, basically here at the end of the period and somewhere here, okay? So say just at the beginning in the middle, so in T1 over 2 and at T1, we have what is called the square wave modulation. And in the square wave modulation, there is no more difference between unipolar or bipolar pulse width modulator, because the only thing that happens is that for T1 over 2, so half the period of the output fundamental component, you have TA plus and TB minus on. For the second half, you have TA minus, TB plus that are on. So the two switches that they are opposite in their geometrical representation here acts as a unique switch. TA plus, TB minus, TB plus, TA minus. A and B. This is VD. So for half of the period, TA plus and TB minus are closed, and the other two are open. In the second half of the period, TA minus and TB plus are open. Okay, so they are closed. So if you look at TAN and TBN, basically you have that VAN over T is something like this. Okay, and VBN, so the voltage here and here, okay, and of course V naught, which is the difference between the two, V naught is VAN minus VBN is the difference, and this is what I showed you before. This is T1, and this is T1 over 2. T1 over 2, T1 over 2. This is V naught. Okay, this is what is called square wave modulation. So I put the peak value of the triangle of the frequency component, fundamental frequency component of the output versus MA, okay? Summarizing what I said up to now, we have a linear range of variation in which at the maximum you can obtain VD, and you can obtain VD as the maximum, linearly varying the amplitude of the control voltage. Okay. Then you have an intermediate situation in which the control voltage is allowed to exceed the peak value of triangular waveform, in which you can increase a little bit this output voltage up to a certain point in which, let me call this MA star, and this MA star depends on the frequency factor on MF, basically, in which basically you have just, say, intersection between the control voltage and triangular waveform at the beginning, at the half the period T1 at the end of the period, in which you have, say, the square wave modulation. You can have this behavior. What is the output spectrum of this waveform? This waveform is exactly a square waveform. Square waveform means that duty cycle T is exactly 50%. So you have a square waveform like this, and it's easy to, say, derive the spectrum of a square waveform, because this spectrum is given by the odd harmonic, the odd harmonics of the fundamental, which is F1. Okay, so you have F1, and then you have 3F1, then you have 5F1, then you have 7F1, 9F1, etc. Only odd harmonics, and which is the amplitude of these harmonics. But basically you have that the amplitude can be described in this way. This is V, not H. H is an integer giving you the order of the harmonics, okay? Because you have H is 1, is the amplitude of this waveform here. And then you have V, V naught 3, etc., etc. This is given by 4 Vd over P multiplied H. So this is, for example, the first one is 4 Vd divided P. The third harmonic here is 4 Vd P divided by 3, 4 Vd P divided by 5, etc. So this amplitude here is decreasing up to very small values. Okay, so this is the amplitude. So what is the maximum amplitude that you can get here? It is 4 Vd over P. And what happens if you increase MA, say, to larger value than MA star? Something changes in the amplitude. For example, let's have a look to this. This is the standard triangular waveform. Then I have my control voltage here. Okay, so for example, you have this behavior here. What happens? This is for, say, MA star. The control voltage has exactly the behavior for which I cannot have no more comparison. What happens if I increase again? Something changes? No. The situation provides you always for any MA larger than MA star, V naught is always this one, VD negativity. There is no change in this. So it is not useful to increase MA over this value, over MA star. The output voltage is always the same, the spectrum is always the same, so it means that here you reach a saturation level. Basically, in the square wave region, you have no variation of the input. You have here the overmodulation, and this is the linear region. Okay. Maybe we can have a little break, 10 minutes break, then we continue from this point on, okay? So let's have a 10 minutes break, 1 and basically 10 we can continue. Okay, we were talking about the square wave modulation. The square wave modulation has some, let's say, specific features. First of all, so let me summarize in this page, square wave modulation. So first of all, is it a square wave modulation a pulse width modulation? Look at this, the waveform I obtained at the output. We cannot say that the square wave modulation is a pulse width modulation at all, because basically what I get at the output is simply a square wave having frequency f1 with duty cycle 50%. There is no more width modulation of the output depending on the amplitude of the sine wave that you use as a control voltage. Okay, there is no more, say, behavior like a output voltage which is sine wave modulated. There is no more, let's say, this benefit of the comparing the triangular waveform at the modulator with the control voltage, which is this sine wave. In this case, we lost totally the possibility to get this kind of comparison. So this is not something that we can categorize under the pulse width modulation. Okay, the output is this one. Okay, this output here, and this is what we get independently of the frequency of the triangular waveform, and basically independently on the amplitude of the sine wave, if this amplitude is higher than that give us MA star. So basically this is not obtained by using the pulse width modulator, which you have the triangular waveform and the control voltage, as I explained to you when we talked about the pulse width modulator. Okay, so I derive it in this way. Okay, my derivation here is pure theoretically derivation. Okay, I start from a pulse width modulation in which you get this, say, modulator, which you have triangular waveform and a control voltage, which is a sine wave. Okay, then I move step by step using the same, say, approach to a situation in which this kind of modulator is no more, say, helpful. In the square wave, you don't need to have this kind of modulation. What you need is simply to modulate these two transistors, TA plus and TB minus, and these other two, TB plus and T minus, as they were just a single switch with a duty cycle of 50% and a period which is exactly the period you want to get at the output, so the frequency f1. Okay, no more than this. Okay, there is no need of control voltage, you don't need to have any triangular waveform, etc. Okay, in terms of if you want modulation, generation is very simple. Okay, simply switch on and off the pairs of switches that are indicated there with this frequency. Okay, so basically this is no more a pulse width modulation. It is no longer a pulse width modulation. Look at what happened. Okay, look at this output waveform that I have here. What I can change in the output voltage? I mean, if you change the T1, okay, which is the frequency of this switching action I just described to you, I can change the frequency F1 I can have here. So basically, I can modulate the frequency of the output fundamental component. This is possible, exactly as I was able to modulate the output frequency in pulse width modulator or in overmodulation. Look at the output voltage, the peak value of the fundamental component, V01. V01 at frequency F1 is this 4 Vt divided P. It's something that you can modulate in some way. You can change depending on the need you are requiring for the output. Basically, this quantity is fixed. Okay, so with the square wave modulation, you cannot change the amplitude of the fundamental component. So the amplitude of fundamental frequency component of V naught is fixed at Vt 4 divided P. Okay, you cannot change. It's not possible to change. So I can change the frequency, but I can change the amplitude. This is something that I was able to do in pulse width modulation, okay, and also in overmodulation. Okay, changing the amplitudes, changing MA, give us the opportunity in sinusoidal pulse width modulator and overmodulation to also modulate the amplitude of the fundamental component of the voltage. Here, this is no more possible. Okay, so which way I can modulate the amplitude if I need for my application? But what happens is that I have to add something at the DC input of my square wave inverter. If I have here the square wave inverter, this is the voltage VD. As you can see, the amplitude of the square wave depends on VD. So I have to put here a block, which basically is a DC to DC converter. By which I can change, let's say, VD plus VD prime to a voltage VD. Okay, this converter can be, I don't know, a buck converter, yes, step-up converter, a boost converter, whatever, in order to make it possible to change the voltage VD. Okay, here. So if I change the voltage VD, I change also the amplitude of the fundamental frequency component at the output. The only way is to add something that changes the voltage VD, because if the voltage G is fixed and I don't have any means to change it, then I have to accept this as the maximum possible and constant frequency component at the output. Other characteristics that we can see in this behavior here, here we have TA plus and TA minus on, and then we have TA minus and TB plus on. How many switches you have in a period T1? Basically, you have that after the period, the red transistor are on, and then they simultaneously switch off, and they becomes on TA plus and TA minus and TB plus. So there are basically just one switch action here during this period T1. So in terms of power dissipated by switching activity of the transistor, this solution gives the less amount of power dissipated during the switching activity of MOSFET. Okay, compare this situation in a period T1 with respect to that you have, for example, for linear pulse width modulator. There you have switching activity at the switching frequency, Fs, okay, which is much higher than T1. So in terms of dynamic power, the pulse width modulator is something that dissipated large power with respect to this one. So low power dynamically dissipated by transistor switching, because you have less commutations, okay, during a period T1. Look at the output spectrum. The output spectrum here is this one. Okay. Can you say that this spectrum is easily to filter out? Okay. Suppose that you want to obtain at the output, you want to just get the fundamental F1 and to get rid of all the other high order harmonics, like for example this one. Okay. Your low pass filter that you have at the output of your inverter should be able to, let's say, have a very steep response between F1 and 3F1. So it means that it is maybe is not enough LR filter which is based on the parasitics of the motor you are driving. Maybe you have to add a second order filter, or maybe a third order filter in order to do that. So in order to get very high quality of your output voltage, so you get very low total harmonic distortion, so you get a very pure sine wave at the output, then you have to have a very large filter, very, say, steep filter at the output. So you can say that filtering higher order harmonics is difficult. Now, this means that, for example, this kind of solution will be typically employed for all that application in which you are not too much worried about having ripple in the output current, so ripple in the torque, vibration, noise, acoustic noise, etc. And while this property here that you have very low power dynamically dissipated is something that suggests that you can use this kind of modulation, square wave modulation, for application that manage very high power rating for the power delivered to the load, in which you are employing, for example, transistor or thyristors that are very slow. So transistor or say thyristors, like for example the S here that I showed you before, that I mentioned yesterday, that are very slow in their switching action, so they cannot switch very fast. And so, for example, this solution is easily adopted for all the kind of devices that have no so fast action in switching between on and off. Okay, so very large power. So thyristors, for example, for say hundreds of kilowatt, etc. Another, let's say, something which is related to this difficult in filtering high order harmonics can be also say indicated by looking at the ripple in the current. Okay, remember that the ripple that you can have in output current is something that is related to a not so good filtering of high order harmonics. Okay, so I'm expecting that in this case, in which the high order harmonics is very difficult to be filtered out due to the density in the spectrum, leads to very large ripple in the current. Okay, and this is in effect what happens here. Let me just to share the slide in order to discuss this topic here. So we have this overmodulation, square wave, etc. Okay, here you can see what is the standard steps that we have to perform in order to get the ripple. Remember, we have to compute the voltage ripple, which is the difference between the instantaneous overall output voltage minus the fundamental frequency component, V01. And this is done in the first two plots. Okay, in the first plots, you can see the output voltage, square waveform, frequency T1, and the fundamental component. The fundamental component has a peak which is higher than Vd, of course, because we are in the square wave. The difference is the V0 minus V01 is the ripple, and the ripple has this behavior here. Now, if you look at the area under the voltage of the ripple, and then you integrate this quantity here, you get the ripple. Okay, as you can see that this area is very large because this is T1F, this is T1. So this section here is a fraction not negligible of T1F. So this area, this triangle has a base which is very high. But basically, this area here is very large, so the ripple is, say, much larger here. The ripple here is much larger than that you can have in pulse width modulator, in which basically these output voltage are several slices, okay, due at frequency Fs. So there are very large number of notches that makes this area here divided into, say, sub-intervals, providing you very small ripple. So the ripple here is very large. And this can be, say, understood simply by graphically, just to understand which is the output spectrum, which is this one, okay, which is populated by a large number of harmonics. Okay, so this is what happens for the square wave modulation. I repeat myself, this is not a pulse width modulator. My derivation is just something that helps you to understand what happens in MA. But in square wave modulator, the square wave modulation, square wave inverters, there is no pulse width modulator block, okay, comparing the triangular waveform with a sine waveform. Okay, so let me just, let's say, include this square wave modulation into a specific class of inverters. Okay, so the square wave inverters can be regarded as a specific case of a class of inverters, which is, let's say, much broader, which is called the harmonic cancellation or elimination inverters. Okay, so this is a broader class of inverters within which we can find also the square wave inverter previously indicated. Basically, what is important here is the main goal for this class of inverter is that we are searching solutions for eliminating some of the harmonic lines you get at the output of a square wave inverter. Okay, So square wave inverter are this kind of output spectrum, this one. What happens if I able to eliminate totally these harmonics for the output spectrum? Of course, I'm making easy the filtering of the output voltage, okay? So I'm searching solution for, say, eliminating the first order harmonics that are higher than F1. So for example, the third one, the fifth one, the seventh one, etc. If I'm able to eliminate these harmonics, then my filter reaction will be better, giving us a total harmonic distortion, which is very low. So let me just consider something that I already discussed before for square wave. And this is this waveform here. In the square wave inverters, we have that VAN, VBN are 18 and 118 out of phase waveform, square wave waveform. Okay, VAN is a square wave waveform like this, for example, 0 PT, and the VBN is 180-degree out of phase with respect to VAN. Okay, and the difference between the two provides us the voltage. You know, what happens if, starting from this situation, I make some modification? Okay, so let's start with this square wave behavior. So this happens in square wave. Let me call this VAN. So T1, let me put this in terms of an angle. Okay, so we scale my axis by omega t. So this is 360 now, and this is 180, 0, and this is VD. And this is VBN. Okay, 180, 360, 0, and the output voltage. V naught. Okay, VD, negative VD. This is the square wave solution. Suppose that now I have the possibility to shift this waveform in this way. I can have VAN, and then I shift rigidly this waveform toward the right. Suppose that I have VBN, and then, oh, sorry, VBN is not. This VBN, of course, is this one. Okay, sorry about that. And suppose that I have this waveform VBN shifted toward the left by the same amount. Okay, what happens to the output? Let me draw. What happens here? Let me put, let's say, the waveform VAN, for example, in this way. Okay, I shifted a little bit. Let me put this angle to be alpha. This is omega t. So we have 118 is here. This is 118 plus the angle alpha. Okay, the amplitude is always Vd. This is VAN. Let's go with VBN. VBN is shifted toward the left, so we have something like this. Suppose that I shift with the same angle, which is alpha. So we have negative alpha here, and we have 118 minus alpha here. PD. What happens to the output voltage? The output voltage will be, this is 180. The output voltage is given by the difference between VAN and VBN. And so it is so we have 0 VD. This is alpha. This point is 180 minus alpha. This is 180 plus alpha. Negative VD. This is 360 degree. And so this space in which you have null here is 2 alpha. Okay, so you have you introduced in this way an interval in the output waveform in which you have a third level, which is 0 for the output voltage. Okay, previously you have no this value. Okay, the voltage is just 2 level voltage, negative VD plus VD. Now it happens that I'm able in this way to introduce these other intervals. So you have here, for example, TA plus and TB minus that are on. We have here TA minus and TB plus that are both on. And in between we have, for example, TA plus and TB plus that are simultaneously on. And then you have TA minus and this is TB minus that are simultaneously on. So these two 0 level are obtained by both the high side transistor or both the low side transistor to be on. More or less typically the switch combination that we have in the unipolar parts with oscillator. Remember the 4 different status of the switch that give us 3 levels of variation. Okay, so let's now have a closer look to this waveform here, because we want to define, want to compute the spectrum of this voltage. Okay, understand if there is some possibility to, say, simplify the output spectrum, eliminating some harmonics. Okay, so the output voltage, which now I have to redraw here as this behavior. VD 0 negative VD. This is alpha. This is 2 alpha and this is 180. 360, etc. If you look at this waveform here, you can recognize this waveform as odd symmetry. Odd symmetry means that for a function ft, that if you want to have f of negative t, this is negative f of t. Okay, and this happens in this waveform. Okay, for example, this waveform has this behavior for negative omega t. Okay, for example, this point here, which is f the negative, say this angle here, negative omega t here, is obtained by minus or negative f of t here. So this is a typical odd symmetry waveform. Then it has another symmetry, which is what is called the half wave symmetry. The half wave symmetry is the specific symmetry for which f of t is negative f of t minus tf, the t divided by 2. If the waveform has a period of t, okay, you can get this waveform here. Okay, for example, if you want to verify that this waveform is exactly an half wave symmetry waveform, that typically you have to, let's consider one period, okay, from 0 to 306 in this case. Reverse this, okay, so if I reverse this, I can get something like this. Okay, this is minus f dt, like this. Consider that this is my period t, okay? So shift this waveform by t divided by 2 to the left, okay? And if I do this, I have to shift to the left, so it means that I have something like this, okay? And this is negative f t minus t divided by 2. And then compare this waveform here to the original one. And if I compare to the original one, I can see that ft is exactly negative f t minus t. So these are exactly this half wave symmetry, and it has this odd symmetry. Why are so important these kind of symmetries? Because if you want to compute the spectrum of the output, this waveform, okay, you have to use the Fourier series. Okay? And the Fourier series takes advantage of symmetries in the waveform you are considering. So Fourier series of a function ft is something like f t. Let's have just call it as V naught. Let's have the spectrum of the voltage V naught, okay, directly. This is something like 1f a naught plus summation from h1 to infinite of a h cosine h omega t plus ph sine h omega t, in which a naught, ah, bh are all coefficients. These coefficients can be computed by these formulas. IH is, let's say, 0 to 2p 1 over p of the voltage V naught cosine h omega t This for h ranging from 0 to the infinite. And bh is computed as 1 over p, the integrals over a period v naught t sine h omega t the omega t, again for h0 to infinity. Okay, so these are the coefficients of the Fourier series that we have to use for computing this output spectrum. Okay, so what are the advantages that we have having that specific symmetries? Okay, so if you have a waveform that has odd symmetry, this leads exactly to have no AH coefficients. So basically all AH are null. So these components here are null. Including this one, of course. If you have a half wave symmetry, you have that AH is null, but this is also true for BH. For H even number. Okay, so we can exploit exactly these two characteristics. Okay, and using these two characteristics for our waveform, we can have that our Fourier series is what? So for the odd symmetry, we don't have this one, and then we don't have any cosine terms. Yes, I have a question. On slide is for odd number. Let me check. Odd h. No, it is the even number here. For any even number, you have, if h is an even number, you have 0. So what happens that you have just in the summation only odd numbers. This is what for sure. Maybe I have say something wrong in my slide. Let me check. Yes, there is an error in the slide number 30, in which you have AH equal to BH 0 for odd H. No, it's for even H. For even number is null. What remains is just the odd number. Okay. So let me consider what happens here. So simplifying my output voltage V naught, I have no more these two cosine terms, and say this is the average value. Okay, this is the DC value. Okay, I have a waveform which has no DC components. I have just this term here, okay, in which H should be odd. Let me put in this way. BH sine H omega t. Okay, this is my Fourier series for the waveform I had before. Now we have to compute this BH amplitude. Okay, these BH are exactly the amplitude of each harmonics, okay? And we have H is the number of the harmonics I have, and just here I can recognize that I will have just odd harmonics in the output spectrum, okay? So BH is, let me consider what happens here. Okay, BH is this coefficient here, and let me also consider the waveform. This is the product of the voltage I have multiplied a sine wave. Okay, so what is the waveform? Is here. It basically I can consider the integral is extended to all the period from 0 to, say, here to 2p. Okay, I can also consider that since my waveform is multiplied by a sine wave, okay, and this sine wave is positive for this half period and is negative for the other one, so I'm multiplying basically two positive quantity for half the period and two negative quantity for the other half of the period. So basically this integral is the same as 2 times p. The integral is just extended over a half the period because I'm counting 2 times that product. H omega t, the omega t. Okay, so now this integral for BH is extended just over p, just over half the period, so it's extended up to here. But in this interval here, there are two intervals that are this one, in which the function V naught is null. So my integral just to be extended between alpha and 118 minus alpha. So BH is 2 over P. Let me consider alpha and P minus alpha of Vd sine H omega t in the omega t. Okay, so simplifying, pH is 2 Vd over P integral of alpha P minus alpha of a sine wave. This is a simple integral of a sine wave, so I left for your, say, computation if you want. It's nothing that is impossible to solve. What happens here is that result give us 4 Vd over Ph cosine alpha H. H, which is odd number. So these are the coefficients of my output spectrum. So let me plot the spectrum, okay, that I just computed. I have the fundamental component F1 that I obtain by using H number 1. Okay, so if you want, H is 1 here. And so I have the amplitude, which is 4 Vd over P cosine of alpha. Then, since H is an odd number, the other harmonic is the third one. And then I have 4 Vd over P3 cosine of 3 alpha. Let me just put here the fifth one. So H is 5, 4 Vd for 5 b cosine 5 alpha, etc., etc., etc. So first consideration that I can have looking at this waveform, if alpha is null, what happens to my waveform? If alpha is null means that this angle does not exist. And so I have exactly the square wave inverters previously commented. Okay, so in that situation, you can see that my description here includes also the square wave. Okay, and if I have the square wave, put alpha in this expression of the harmonics, and you can see that you have exactly the spectrum I gave you before for the square wave modulation, for Vd over P, etc., etc., etc. Okay, because the cosine of 0 is 1. If alpha is different from 0, then we have some, let's say, interesting situations. Okay, for example, let's consider the case in which alpha is P divided by 6. So this is 30 degrees. What happens? Let me consider the first amplitude, so B1. B1 is 4 Vd over P cosine d alpha. And this is 4 Vd P square root of 3 divided by 2. What happens to B3? Is 4 Vd P cosine of 3 P6 0. So the amplitude of the third harmonic is null. What happens to B5? B5 is, I don't know, 4 Vd P cosine 5 P6 is not null. But basically, etc., etc. If I choose to have this alpha, my output spectrum is a little bit simplified because I have F1, I have no more 3F1, I have 5F1, and then I have 7F1, 9F1, etc., etc. But basically I have no harmonic here. So I have a space between the F1 and the fifth harmonic here. And this makes possible to reduce the constraints on the output filter in order to get just the harmonic at frequency F1. Okay, because now the first high order harmonic with respect to F1 is the fifth harmonic, it's not more the third one. Okay, so alpha 30 degree makes possible to eliminate one of the harmonics. And this makes, say, a solution. Also, this is the reason why this is also called a voltage cancellation or harmonic elimination inverters. Okay, so choosing exactly alpha, which is the drawback. The drawback is that if you look, for example, the amplitude of the first component here, that is given by this expression here, then this quantity here is a little lower than the value you have for, let's say, square wave modulation. Okay, so I'm accepting to make easy the design of the output filter, but I have to consider the fact that my fundamental component at the output has an amplitude which is a little bit reduced from that you can have in square wave. Let me just show you what I put on the slide, because there are some drawing. that I can comment on. Okay, here, for example, you can see a plot here in this lower side of the page that show you the total harmonic distortion. Okay, the total harmonic distortion is a measure of the contribution of the higher order harmonics with respect to the fundamental one. Okay, of course, for example, a pure sine wave has a total harmonic distortion of 0. A very distorted sine wave, so in which the high order harmonics have a large impact on the, say, waveform that you can obtain, has a total harmonic distortion that can be very large. This is the plot of the total harmonic distortion of the voltage cancellation inverter versus the angle 2 alpha, 2 times alpha. And as you can see, this yellow curve is the total harmonic distortion. So the total harmonic distortion is a little bit lower if alpha is exactly 30 degrees. So 2 alpha is 60 degrees, so it's here. Okay, when you eliminate the third harmonic here, you can see that there is exactly a minimum of the total harmonic distortion. The other cards here represent the amplitude of the fundamental component of the third harmonic, the fifth harmonic, the seventh harmonic, with respect to alpha. Okay, with alpha 30 degrees, so to alpha 60 degrees. So here, the third harmonic is null, the amplitude, while we have again the fifth harmonic and the seventh harmonic. Then, according to this discussion here, you can choose alpha for eliminating, for example, the fifth harmonic, okay, here, or the seventh harmonic here. Is it possible to eliminate simultaneously the third harmonic and the fifth harmonic, for example, because it can be something that is can be much more helpful, because now if you eliminate simultaneously the third and the fifth harmonic, what happens is that you can have F1 and then the high order harmonics is the successive harmonic is the seventh one. So you have, say, much more space for your filter. So the constraints and the characteristics of the filter can be a little bit relaxed. In order to understand why this is not possible, so you can just eliminate one harmonic at a time, okay, typically the third harmonic, but then you can also choose for different harmonics depending on what you want to obtain at the output. Let me just comment on this integral here, okay, the integral given as BH that I just wrote on the whiteboard. BH is the coefficient of the harmonic expansion, okay, the Fourier series, and is given by the product of the voltage V naught and a sine wave. So I can also give a graphical, let's say, solution for this integral here. And what is the graphical solution? I have to put the integral of a product of two functions. Okay, let me put this way. I have the output voltage V naught here, and this is, for example, the third harmonic. Sine of 3 omega t is exactly the third harmonic. Okay, so in this case, if I multiply V naught, which is the rectangular waveform here, with 3 levels, and sine of 3 omega t, I'm just considering V naught multiplying sine of 3 omega t, which is B3. Okay, the product, the integral of that product, give us the amplitude of the third harmonic. Okay, if I have alpha 30 degree, okay, so let's have here 30 degrees, so my waveform is 0 before 30 degree, and then V naught goes to VD, and then I have 60 degree of 0 waveform around 180 here. Okay, look at the multiplication between these two functions. Okay, the multiplication is not null only in this part, because here we have 0, and so product between the sine wave and V naught give us 0, etc. The integral is extended over this half period, as I showed you before. As you can see, this area here, a little, say, darker the positive one, this negative area here exactly has the same value of the two positive areas that you have here. So basically, the summation of these areas is null. And this is the reason why I have exactly BH, in the case of B3, alpha 30 degree, which is null. Okay, because the product of these two functions for alpha 30 degree exactly give us a say a situation which you have, say, an area which is null. What happens if I use the same angle, 30 degree alpha, but not with the third harmonic, with the fifth harmonic, sine 5 omega t? The integral of the product extended to half the period will give us exactly the B5, so the amplitude of the fifth harmonic in the output spectrum. So now I have this waveform here is a sine wave which has 5 omega t, so it's 5 times the period. Alpha is 30, so the V naught waveform is, say, the same as before. And so we have to look to what happens to the product between the two. But as you can see here, simply, say, understanding what happens here is that the negative areas, the summation with these two dark gray waveforms, does not compensate for the positive voltages, for the positive area of the sine wave. So it means that you have a not null integral. So for the same alpha, 30 degree, I can have null integrals, so giving us B3 0, but B5 is not 0. But this is exactly what I just commented before. If I have alpha here, which give us the 0 in the third harmonic, then the fifth harmonic is not 0. What I have to modify in this, say, graphical representation, if I want simultaneously to illuminate the third and the fifth harmonic, but I have to modify a little bit the voltage V naught. If I introduce some notches, so some small intervals in which the output voltage is no more VD, but it is 0, like these two notches that you have in this low side waveform, okay, then I was able, of course, these notches here have computed angles, okay? So for example, here, these notches ranges from 54 degree to 66 degree, and another notches for 114 degree to 126 degree, okay? If I introduce these notches here, now the integral is just extended over these three pulses. And if you look at these three pulses here, then you must be able to, for that specific angle, to see that the green area, positive area, is exactly the same of the, say, dark green area. So now B5 is null. But if you apply the same output voltage V naught with these two notches with the same angle, also to the third harmonic, so this one, okay, you can see that also in this case you have B3, which is 0. So this discussion can be extended in order to eliminate more harmonic lines, okay? If you want to just eliminate one harmonic at a time, okay, choose the alpha which is suitable for you. Typically, this is done for the third harmonic, okay? If you want to eliminate simultaneously two or more harmonics, then you have to compute these angles, okay, in which you introduce specific notches in the output voltage in order to make the integral null for more than one harmonics, okay? So this is just an example, that gives you the possibility to eliminate simultaneously the fifth and the third harmonic. And so the first higher order harmonic is the seventh harmonic. So this is very, so extrapolating this discussion, okay, what I can say that this is something that can be done. This kind of inverters that are based on this angle computation are also known as programmed angle or stored angle inverters, okay? They have these, say, specific angles that they stored in some memories and some, say, specific areas in the digital control of the inverters that makes possible to eliminate this harmonic line. If I want to extrapolate this discussion, I can say if I want to eliminate more harmonics, okay, well, the third, the fifth, and the seventh, and maybe the 11th, etc., what happens is that I have to introduce a lot of notches. And extrapolating this discussion further, eliminating more harmonics, what happens is that I come back to something which is very similar to the pulse width modulations, okay, in which you have, let's say, this behavior, in which you have some notches in the output voltage due to the pulse width modulation given by the comparison between the control voltage and the triangular wave. Okay, so this is my, say, what happens in the extrapolating the discussion for eliminating much harmonics. In effect, if you remember what happens in the output spectrum of the voltage for a pulse width modulator, you have F1 and the first high order harmonic in something around the switching frequency Fs. Okay, so this means that you can come back to something that we already know. Okay, but for some specific application, it will be easy to say have small notches, so not increasing too much the switching frequency and the dynamic losses of the transistors, but anyway making easier the simulation, the design of the output filter. Have you questions, doubt about this this discussion? Everything is okay? Okay, if the discussion here is no, say, there are no questions, we can move to the next topic. Up to now, we discussed the one-phase inverters, okay, and I show you the basic categories in the single-phase inverter that we can have from pulse width modulator to square wave, passing through, say, wave modulation, etc. But a very large categories of inverters is the three-phase inverters. Okay, so let me move to the three-phase inverters. And I need the whiteboard. Three-phase inverters. So basically, I need not just two terminals at the output through which I can have a sine wave, but I need three different sine waves at the output. I have to generate three sine waveforms, and these three sine waveforms must be shifted 120 degrees each from the others. Okay, because this is the typical structure of a three-phase voltage system. Okay, so what I can do for generating these three different waveforms with this specific phase shift, but the immediate solutions is to look at the one-phase inverters. I know that one-phase inverter can generate just one sine waveforms. Okay, so if I have three one-phase inverters modulated opportunely, I can generate three sine waves. Okay, so let me just have these three waveforms, these three one-phase inverters. Forgive me for this discussion. Let me put, say, just a very ideal schematic for the inverter, just the two legs with ideal switches and no diode, but you should understand that switches are transistors, and then you have also the body diode across. The nodes here are A and A prime. Okay, so I have a block here, which is the inverter number A, inverter A, in which you have two outputs that are A and A prime. Okay, and so you have here a voltage V A prime. Let me put here another block, which is the second inverter. The second inverter has output B and B prime. This inverter is the inverter B. And then you have two outputs that are B and B prime, and between these two we have B prime. And then you have a third inverter here, and this inverter has output C and C prime. So this is the C inverter, C and C prime, and between these nodes we have B, C, C prime. These three inverters have in common the supply, okay, because we have VD, the DC voltage, and the DC voltage is the voltage that you can have for the A inverter, is the voltage that you have for the B inverter, and is also the voltage for the C inverter here. So the three inverters basically have the same input voltage VD, and then they have separated output voltage. Remember that the three-phase systems are based on three output voltages or currents: sine wave, three-phase voltages or currents are three sine waveforms having same frequency, same amplitude, and they are shifted in phase 120 degrees each from the other. Okay, this is basically the three-phase configuration. So VA prime, BB prime, CC prime should be three sine waveform, okay, that have the same frequency, same amplitude, but they have to be shifted a little bit one from the other. A little bit, exactly 120 degrees. So how can you obtain this behavior? In order to obtain this behavior, supposing that we are starting our discussion with the sinusoidal pulse width modulator, so linear modulation, we need a modulator, and the modulator is a standard pulse width modulator in which you have the triangular waveform as a fixed frequency and fixed amplitude. Then I have a control voltage for the inverter A. Okay, this is the control voltage V control A. And so basically on the comparison between this control voltage and the triangular waveform, I'm able to generate this output voltage here, VA prime. Then I have another control voltage, which has the same frequency, the same amplitude, so the same MA, but this control voltage should be shifted by 120 degrees from the B control A. So this is something like this. This is B control B, and this is used as control voltage for generating VBB prime. And then I have a third control voltage, which is again same frequency, same amplitude, so same amplitude modulation factor, which is shifted by 120 degrees from the previous two. And this is the V control C, which is used for generating VCC prime. Okay, this is, let's say, basically the idea. Okay, since my goal is to obtain this behavior, okay, I can exploit what I already know. So I can use the linear pulse width modulator in this way, say with three different control voltages that are shifted by 120 degrees. Now we have to consider that three-phase voltages are applied for driving three-phase load. Okay, and typically three-phase loads have a specific configuration. Okay, and the specific configuration are the star connection or the delta connection. So let's start with the star connection of the load. Of three-phase loads. In this case, the loads is, say, configured in this way. So we have an impedance here. Let me call zeta A, and this is the node A. Then I have the impedance zeta B, and this is the node B. This is zeta C, and this is the node C. Okay, so we have three terminals, and then we have these three different loads. This is a representation of a three-phase load star connected. So what happens here? I have three voltages here, and this output A prime, B prime, C prime should be connected to this load. Okay, so one possibility is to have, for example, zeta A connected to the node A and A prime, zeta B connected to the node B prime, and zeta C connected to the node C prime. Okay, so for example, let me move here. It means that zeta E is connected between zeta A connected between A and A prime. So it means that A prime is here in order to have here VA A prime. Then I have zeta B, but zeta B is connected to B and B prime. So I need a node here, which is B prime. And from here, I can have zeta B prime. Then I have zeta C, and zeta C is connected between C and C prime. So C prime is, for example, here. And so I have C prime here. So as you can see, I have to this node not only the terminal of zeta A, zeta B, and zeta E, but something that should be connected to A prime, C prime, and B prime. Okay, so it means basically that this node A prime, C prime, and B prime is common. Okay, so I prime, it's the same of C prime, and it's the same of B prime. So let me consider what happens due to this, say, combination. Redrawing this circuit here in a different way, okay, is a not so huge modification, but it can be helpful for us. This is VD, which is the common input voltage. VD supplies the inverter A. So the inverter A is this one. This is the node A, and this is A prime. Remember that this is red, okay? And this is the inverter A. The same voltage VD supply also the inverter B. So we can put in this way. And the nodes at the output of this inverter are called B and B prime. This is the blue one. Then we have the inverter C, which is again supplied by the same voltage VD. And the nodes are C and C prime. And this is purple. So this circuit here is exactly the same as I plotted here, okay? There is no difference, okay? This is just, say, different way to to show the same concept. So let me consider what happens here. I have that A prime, B prime, and C prime are connected. Okay, so you have that A prime and B prime and C prime are connected. So what does it mean that they are connected? For example, if I consider this switch here, if I close this switch, the voltage between this node A prime and this node N here becomes VD. Okay? What is the voltage between B prime and N? Is VD. What is the voltage between C prime and N? Is VD. So the three say legs that are connected in this way are not, let's say, independent. The switch action of one of this leg, okay, make possible to fix the voltage for the other legs. So this is something that we can call a redundant configuration. We don't need to have all three legs because what happens at the output of these three legs is just decided by the commutation of just one leg. Okay, so it means that, for example, I can eliminate, let's say, the leg C prime. I can eliminate the legs B prime. Okay, since I have no I have this redundant configuration, this dependent configuration, I can see that I can have this leg to be eliminated. Okay, so I can, for example, eliminate this node here. I can eliminate this node here. Okay, now I have that C prime is the same of B prime, and now is the same of A prime. Okay, I have just A prime, and A prime is the reference node for all other B, C, and A node. This node here, which is connected in this way, has specific characteristic, especially if you are in the situation in which you have three loads that are identical. If zeta A is the same of zeta B, and it is the same of zeta C, okay, a situation that we can call just, let's say, at a load which is in equilibrium, okay, in that specific situation, what happens is that the current flowing out of this node is exactly null, okay. If this happens, and this happens most of the time, and is one of the situations that is exploited for three-phase load system, so it means that also the, let's say, the leg A prime, that is the only leg that remains after eliminating the redundant configuration in parallel, can be totally eliminated because no current is provided by this leg. So if no current is provided by this leg, it acts like an open circuit. Okay, and if I have an open circuit, I can eliminate from my discussion. So as can you see, by exploiting the specific configuration of a star-connected three-phase load from the, let's say, 6 legs that I have originally from my discussion started from one-phase inverters, okay, I just have 3 legs. One leg for the, say, the inverter A, one leg just for the inverter B, and the other leg for the inverter C. So this is a configuration that I can use for exploiting, for connecting the load, the three-phase load in star-connected way. Okay. Starting from this, tomorrow morning, 10:30, no, 10, sorry, we can examine what happens if the three-phase load is connected in a delta connection, okay? If there is some changes in the three-phase inverter configuration. Have you questions about this, let's say, discussion, whatever? What if the loads are different, or if the loads are different, then the current exiting from these nodes is effectively not null. And so if you have no null current, basically what happens is that according to this discussion, you need that specific legs. I have to say that this situation is something which is not, let's say, optimized, or something that is not a typical nominal situation for three-phase loads. Three-phase loads are exactly constructed in order to be, let's say, symmetrical and equal between them. So this is the standard situation. When the currents flow, non-null flow from that node, it means that something dangerous can happen. Something is, say, occurring. Okay, so the standard nominal situation is that the loads are always the same. You have an equilibrium, so no current flow in that case. Of course, there are situations this happens, so we have to manage differently from what I said now. Other questions? Okay, guys, if you have no other questions, I can thank you. Have a nice afternoon. See you tomorrow morning.